Okay, we have developed some amount of formalism. We'll continue to do that today. Okay, so we have these state vectors, which we represent by these ket vectors. And we also have special types of ket vectors, which are eigenfunctions of an operator. So if I have an operator A, I have a set of these eigenkets now with corresponding eigenvalues. And we know that these eigenstates correspond to definite values of the measurement. Okay, for these things, for these AIs, and the fluctuation in the measurement is equal to 0. We definitely get AI out of these measurements. So that means yes.
A is an operator, right?
A is an operator, right. So A here is an operator. Okay, let's put a hat on it to make sure that it is an operator. Okay, so if I have a certain measurement operation, A, okay, and here comes my input to the experiment, psi comes in, and what do I get? Okay, I get the possible values of the measurement. I am drawing these lines here, but of course these could be, this could represent a continuum also. Okay, if it's a measurement of position or momentum, for example, then it will be a continuum. But in any case, the result that I get is going to be one of these eigenvalues, A1, A3, etc., up to possibly AN. Okay? And when I make this measurement, I find out that the particle is in state with eigenvalue equal to, say, A2, then the state of the system is eigenstate A2. Okay? So this is now moving on, and suppose I feed this into some other experiment. Okay, so now I'm going to measure the parameter B. Now this B itself is going to have, in general, its own eigenvalues. So I have here B1, all these possibilities, B2, B3, etc., up to some Bn. And when I measure this, I find out perhaps that the value of the B measurement gives me B3, but now the state of the system has collapsed into this B3 state. Okay? Now, what happens if I now go back and measure A again? Okay, so I measure A again. Now, you see, I have lost this eigenstate. So I have, again, a probabilistic outcome, okay, possibly A1, A2, etc. Okay, so all of these things are now possible. Okay? Now, there is a special case, if you like, an exception, in which the eigenstates of A and B are the same. So it is possible, so let's put a big if, okay, I have a case in which A times eigenstate of AI gives me AI times AI, okay, and at the same time, B on the same eigenstate, okay, on the same ket, gives me its own eigenvalue, but it's still an eigenstate. Okay, so obviously this bi will have units of b. Okay, so these are my operators again. So a will have units of the measurement a. Okay, b will have units of measurement b. So they are going to be different eigenvalues. They can have okay, different numerical values and also units, but the eigenstates are the same. Okay, so this, okay, in English we would call it if A and B, okay, share the same eigenstates. Okay, so if A and B share the same eigenstates, then what happens? Well, let's do our experiment again. Here comes an initial psi, which I have very little idea about. Then I make a measurement A, and out comes, okay, possible results, A1, A2, A3, etc. Okay, A4, suppose this time I measure that the outcome is A3. Okay, so the system is now in state A3. But now this is a nice definitive state for the B operator as well, because A3 is an eigenstate of B with eigenvalue, okay, B3, whatever it is. So it's going to be, okay, possibilities are B1, B2, B3, etc. But now this time I'm going to get B3 out definitely, okay? So this is going to be a definite result because the system is already in an eigenstate of B, okay? Although I have labeled it as A3, okay, it is still in the same eigenstate, okay? Now if I do the A measurement again, well, this is already in the state. It doesn't, this B has not done anything to the measurement. Okay, it has not altered it. So I again get A3 out. Okay, so you see which way I put these operators, which measurement I make, first and second what, doesn't matter. Okay, so all of these things give us the same measurement. So once the first measurement is made, these measurements, further measurements by B and A does not disturb the state anymore because it is already in its eigenstate. Okay, if I have an A measurement and then a second A measurement, obviously I should get the same thing, right? That's what measurement means. I measured something. Okay, if that keeps on changing, it's no good as a measurement. Okay, measurement means I measure something and I know what it is. Yes?
How can different observables share the same eigenstate?
Okay, well, how do they share? For example, momentum and energy for a free particle have the same eigenstate, right? For a free particle, this e to the ikx has an eigenvalue of k times h bar. But for the energy, the same eigenstate has the energy, is the eigenvalue h bar squared k squared over 2m. So you can have such things.
I have a question.
Yes.
We said that if we observe AI, then the system collapses into AI
Yes.
as the states. But what if two states have the same eigenvalue?
Well, it still collapses to one of them. Okay, so you make a measurement. Well, okay, you make a measurement if it is a degenerate state so that they have the same eigenvalue, then of course you measure the eigenvalue and you are not sure really which one and with what contribution you have from the two or more eigenstates. Okay, so it still collapses to that set of states, that same eigenvalue, but it will be in general a linear combination of all of them. Now it is possible that one of those eigenvalues are shared, okay, one of those eigenstates are shared with B, and the second one may have a different eigenvalue, okay, just as in the case of the energy. I measure the energy of the free particle, I get some value, Okay, but just from the energy measurement, I don't know which direction the particle is going. Okay, so I need a second measurement to find out in which direction the momentum is. Okay, so yes.
Professor, does the eigenstate and eigenvalue refer to the same thing? I mean, for example, for energy, for previous lectures, we said that we assume that there is a different energy states.
Mhm.
For example, E1 is equal to
Mhm.
operator or something like that. So can we say that eigenvalue is the eigenstate? Eigenvalue is determined by eigenstate.
Well, yes, eigenvalues and eigenvectors have a one-to-one correspondence. Okay, perhaps that's the best way of saying it. Okay, so you have, for a system, for an operator, you have a set of eigenvectors, and each one of them will have an eigenvalue. Okay, so this is actually the mathematical statement of it. For each operator, you have these eigenvalues, and those eigenvalues have corresponding eigenstates. Okay, so those eigenstates may also be shared by other operators, but then they'll have different eigenvalues. Yes.
For the Hamiltonian operator, the eigenvalues are ENs, right?
Yes. Okay. Yes.
Notation-wise, A subscript I refers to eigenstate if it's inside the ket and it's outside the ket.
Yes. Okay. So maybe I should emphasize that more. I'm writing these AIs like this. So AI means an eigenstate corresponds to an eigenstate of the A operator. If it's inside the ket, okay, that means it represents the ith state. And if it is outside, if it's just a number, then it's the eigenvalue. Okay? Because we'll use eigenstates from various operators, so you'll have to make the distinction. Okay? Okay, let's go on. Now, what happens? Okay, let's just see what is happening with these operators. Okay, so if I have an operator A, okay, operating on this object, and then the operator B is operating on the same object, okay, which is going to be my state psi. So according to this, okay, so we are still under this if. We are still looking at the cases when they share the same set of eigenstates. Well, what does this lead to? Let's see. So to make an expansion, what I want to do is I want to expand this psi in terms of the eigenstates of A. Okay? So how do I do that? Well, now that we have this nice notation, it is extremely simple. All I do is expand this psi in terms of AI. So I insert an identity. So AI, right? So eigenstates of this operator form a nice orthonormal set, okay? And if I just sum this over all I, then this is just identity. Okay, we'll keep doing this again and again, okay? So, and it operates on psi. So I have just expanded psi in terms of eigenstates of AI. You see this notation is so nice and compact, I don't have to write integrals, etc. The integral is hidden inside here, okay? So this is a function, okay, which corresponds to an eigenvector of A, inner product with psi. Okay, so this is just a number. This is the expansion coefficient. This is what we used to call the CIs times the eigenstate. Okay? Yes?
In this case, we are assuming that eigenstates are discrete, right?
Well, yes. Okay, so again, a nice thing about this notation is that if I come halfway around algebra and say, well, I really meant continuous, this then is just an integral. Okay? So these summation signs and integral signs in this notation are interchangeable. Okay, so if it is discrete, I put a summation. If it's continuous, I put an integral times dx or whatever. Yes?
We can assume orthonormality only if the they are Hermitian numbers,
Yes,
right?
yes, okay. So we are associating them with measurements, which means that they have to be Hermitian. Okay, so their eigenvalues are real and everything. Okay, yes.
You have given the example of a free particle saying the eigenstates will be the same,
Mhm.
but isn't that always the case, and if not, why? If so, still why?
What do you mean?
Energy and momentum has the same eigenstates for a free
For
particle.
pre-particle, yes. Uh-huh.
But in some cases, it doesn't. They don't have the same eigenstates. Is that the case?
Well, for a free particle, it's always the case. But if you are a particle in a box, then you know the energy eigenstates are these sine functions, right? Sine and pi, say, and they are not the momentum eigenfunctions.
Okay, but what breaks that?
What?
What exactly breaks this?
What breaks it? Okay, you see, what breaks it is that you no longer have translational, independence in the case of a potential. If you have a potential, then the system is not translationally invariant, which means momentum is not conserved in general. Okay, so in that case, we will actually specify it much more precisely. Other questions? Okay. So let's go on. Now, this AI is an eigenstate of operator A. So I'm going to get B, okay, summation. A times AI is eigenvalue AI times AI. So it's going to be AI, okay, AI psi. And then B operating on AI, but that also gives me an eigenvalue, right? So that's very nice. What I get is I, BI, AI, okay, AI, then I have AI psi. Right? Now let me do this in the reverse order. Let me make it A times B operating on psi. Okay? Well, it's just going to be the same sort of algebra. A, B, okay, sum over I, AI again, AI psi. B times AI, since that's an eigenvector, is going to give me, okay, A times BI times AI psi. And I have this A operating on AI now, so that's going to give its eigenvalue. So that will be sum I, AI, BI, AI psi. But this is, okay, since these are just two numbers, these two numbers are equal to one another. And that means I have, okay, this BA operating on psi gives me something. Okay, psi is a very general vector. AB operating on psi gives me exactly the same thing. So as operators, they are indistinguishable. Okay, they take something and give you something else, but the second one does exactly the same thing. So that means if that's the case, let's put a then here, then A, B equals B, A. Okay? So if A and B share same sets of eigenvectors, then the two operators AB and BA are equal. Or another way of saying it is that A and B commute, right? Because this is equal to AB minus BA. Okay, and that's Okay, in English we would say A and B commute. And from the perspective of the experimental setup here, we say, okay, A and B are compatible. Okay? Yes.
A and B commute, does that mean A preserves B? For example, if B would be Hamiltonian and A would be any operator, and then treating the state with the A operator does not change the whole energy of the state.
Yes. Yes. Okay. So if we'll look at special cases, the commutation with Hamiltonian would mean that the okay. So let me also put this in reverse. The reverse is also true. Okay. So if A and B commute, then they share same sets of eigenvectors. Okay. The proof of that is a little bit more lengthy, but I'll leave that as an exercise to the class. If two operators commute, then they share same sets of eigenvectors. Okay, so if something commutes with the Hamiltonian, what does that mean? That means the Hamiltonian and that operator share the same eigenvectors. Yes?
So what do we mean by compatible?
Okay,
I understand commute, but what is the compatible?
Compatible is just the description, okay, English word description for this case. Compatible means, okay, compatible, if you, I don't know if I should say this, but if sometimes we say, okay, this is a nice guy and a nice girl, but they are not really compatible, which means, okay, the relationship is not going to go that well, perhaps. That's your prediction. So if two operators are compatible, they can get married. Okay, so. Okay, other questions? Yes.
Can you explain the relation with commutations value and the second observer value in that? For example, if it is 0, obviously it will be 1 and 1. But if it's, for example, I know IH or...
Okay, so that's what we are going to do next. Okay, so what we have here now, suppose A and B, okay, so let's put that down. Suppose two operators A and B do not commute. Okay, they are incompatible. Okay, so they are two incompatible operators. So they have their different eigenvalues and eigenvectors. Now, and now here I have some psi, and I want to make a measurement. Okay, I have the possibility of making two different types of measurements. I can either make A or B. Okay, so I have these two possibilities. Now, I can do only one of them. Okay, I cannot do a simultaneous, I cannot break up a state. Okay, so it either goes to A or it goes to B. Now, this has certain possible outcomes, and this one has a set of outcomes, possible outcomes, right? So, each one of these things have certain probabilities. So I can just make perhaps a probability plot of what this A is going to be, and this is probability of A in this direction, and this will have a certain probability, right? And we know how to calculate this. And what about this B? Okay, so I have a certain probability of getting a certain B, and that's going to be some other function. All right, so for each one of these things, I have a certain average value. Okay, so this is going to be, say, the average value of A for this psi, and we have an average value of b for, again, the same psi, okay? Because average values, remember, depend on the wave function or the state of the system, right? It's just equal to psi a psi, right? So same thing here, psi b psi. Now, I also have a certain amount of uncertainty, which we have calculated, we have specified as delta A, and there will be some, again, uncertainty here, which we are going to call delta B. So there's some uncertainty here and uncertainty there. Now, these things all depend on what psi is. For example, I can just arrange everything so that this psi is one of these eigenstates. Okay? If I choose as my incoming psi one of these eigenstates, what will my delta A be? Zero, right? Because then I definitely will measure that value, okay? But then, of course, I'm going to get something else here, okay? Now, there's this nice theorem which tells us that this delta A, delta B, is greater than equal to 1 over 2, okay, magnitude of this expectation value of commutator of A and B. Okay, so let's just look at these terms one by one. There's a commutator of A and B. Okay, all of these things are with respect to the same psi. Okay, we don't usually put a subscript here, but these are all with respect to the same psi. Okay, these deltas and the expectation values. And it says that the uncertainty in A times the uncertainty in B is greater than or equal to 1/2. You take the commutator. The commutator in general is another operator. You take its expectation value, okay? Then take its magnitude multiplied by 1/2, and that's your uncertainty, okay? So this is called the generalized uncertainty relation. Okay, so the proof is in Griffiths, okay, a one-page proof, which I'm not going to duplicate here because physically it doesn't really contain anything very much, but the result is very important. So as an example, okay, I can take as the A operator the momentum operator. For the B operator, I have the, say, X operator, right? So that I have momentum and position. So this says that delta X, delta P is greater than equal to 1/2 magnitude of commutator of X and P. Okay, the way I have written it is P and X, so it's going to be minus I H bar, right? This time I don't really need to even take an average because this is a constant. Okay, expectation value of the constant is just itself. And then I have the magnitude, so this is just equal to H bar over 2. Okay, so this is a very nice physical result which tells us if I have incompatible operators, what the uncertainty will be when I try to make this measurement. Now, if the operators are compatible, okay, if the operators are compatible, then, for example, this just becomes 0, and the example of a case where I would get 0 as delta A times delta P would be to choose one of these eigenstates. If I choose one of these eigenstates as my psi, then for that particular case, I am going to get certainly one of these things, okay, the corresponding eigenvector. So there will be no uncertainty in the result. But since this is also an eigenvector of B, again, I'm going to get a certain definite result. Okay, so I'm going to get definite both cases. Yes. No, you first, because I decide who goes first. Okay.
If we do the same thing when A and B are not compatible, if we send the eigenstate of A, then the uncertainty in B would be
Yes.
infinite, right?
Yes. Yes. Yes.
Does the compatibility of operators depend on the orthogonality of their eigenstates? Can you say something like that?
Well, they not only orthogonal, they have to share the same eigenstates. They have to have the same eigenstates. Okay?
I mean,
So-
not compatibility.
Oh, okay. If they are not compatible, then of course it depends on the operator. Okay? It depends the amount of incompatibility. So this is really a measure of the incompatibility. Here we get h bar over 2. You are going to get something else for different operators. Okay? Any other questions? Yes.
How do you define delta A, delta B for a discrete
Okay, delta A, delta B is just you take this psi. Remember that, okay, I already wrote down what average value of A is. Okay, it's going to be psi A psi, right? I also take the average value of A squared, which is going to be psi A squared psi, right? And if I know these two, then delta A squared is A squared minus A squared. Okay, so that's the definition. Yeah.
Then, is it possible to associate number of resulting eigenvalues with commutation? For example, if we get one eigenvalue and one eigenvalue for A and B, let's say we get 1 and 2, and or 1 and 3. Like how do we associate the resulting number of eigenvalues with commutation? Can we? Or I don't know.
Okay, I don't know if I understand the question, but the operators are either compatible or incompatible. It's by if accidentally they have, I don't know if that's even possible. What happens if there's just accidentally one eigenvector that is common to both? That probably would not happen because that would be against this theorem, because then you would get zero uncertainty even though they are incompatible.
What I mean is, can we define closeness of the eigenstate with the commutation relation, but with the number of...
No, the eigenstates, you see, the eigenstates are not really close to one another. Okay, you have these eigenstates, whether it's A or B, they have to cover the whole Hilbert space. Okay, so the eigenstates of A cover the whole Hilbert space, then they are all orthonormal. So if B is not compatible with it, so B is another set of orthonormal states which covers the same Hilbert space. Okay, so it's very difficult to associate any sort of closeness between them. It's not also very useful. Okay, other question? Yes.
You said it becomes 0 times infinity, but it also the equivalence relation varies a lot because the commutation is not always IH, for example. It's sometimes bigger and lower. So can you quantify that from the infinities you get, looking at the zeros?
Okay, so you are looking at, you are asking about an extreme case when you approach definiteless on one side and indefiniteless on the other side. Well, you can probably not, okay, not from this relation actually. you may want to calculate it, okay? So you can calculate and see what it is, but this doesn't tell you that. This just gives you a minimum amount of uncertainty that is valid, okay? So you don't know how much bigger it's going to be. For things like that, it's more economical to actually calculate delta A and delta B and see how they behave, okay? Okay, what else? Something is missing here is a clock. Thank you. All right, so what do we do? Let's, yeah.
By the way, about two operators having just a single eigenvalue, same and others different, I think it's not incompatible with commutation relation.
Well, that I'm not so sure about, because if I have just one if I have just one state that is common to both of these operators, I can choose my psi as that state, in which case I'm going to get 0 and 0 for delta A and delta B.
But for that state, the expectation value of the commutator is also 0 with respect to that state. So we have 0 greater than or equal to 0, which is
Okay, yes, good point. Possibly, yes. Okay, so that's actually a good point. Yeah, for a very special case like that, you would have 0 uncertainty, although the operators in general do not commute. Yes. Okay. So what do we do next? All right, let's look at the commutation with H. Okay, so let's also look at time dependence of expectation values. Okay. All right, so what is the expectation value of some operator A with respect to some state psi? Okay, so we write that as psi A psi. Now, what happens to the time dependence? So I'm interested in how this is changing as a function of time. Well, psi in general changes as a function of time. How does it change? Well, it changes according to the Schrödinger equation. So dt psi is equal to h psi. Okay? So there's time dependence hidden in this psi, hidden in that psi, and we have not really seen any such operators, but some operators may be time dependent. Okay, so if you have a time dependent potential, for example, that would happen. Although, okay, we are not going to use such potentials until the second semester. Let's keep things general. So there are 3 places where I differentiate this. dtt psi, right, operating on a psi, plus this psi, and in the middle I have this dA dt psi, and finally plus psi a d dt psi, right, A operating on this. Okay, so let's put all of that stuff in. Now I need the time dependence of a bra vector, so I can just take the adjoint of this equation. Okay, so if I take the adjoint of this equation, what do I get? Well, let's just look at the ordinary ket vector first. d dt psi is 1 over I h bar. h psi. Okay, if I take the adjoint, then the dt of psi is I goes to minus I, remember, I h bar. H goes to h dagger, okay, but h itself is Hermitian, so I don't have to worry about that, okay. Normally it would be the adjoint of h, okay, and I have something like this, okay. So let's put all of those things in. So this is going to give me d dt, this psi, which is minus 1 over I h bar psi times h, okay, and then the rest of the equation, a psi, okay, plus the expectation value of dA dt with respect to the psi state. And then I have plus 1 over I h bar, okay, psi a dagger h psi.
H is an operator, right?
Yes, A is an operator, okay. H is an operator. H is the Hamiltonian operator, but sometimes. Okay, at some point I'll just stop dropping these hats on operators because we are not going to go back to the original space which we analyzed Schrödinger equation. So from now on we'll work only with Dirac notation. So at some point I'll drop certain redundant nomenclature. Okay, so what do I have? I have 1 over I h bar expectation value of AH and HA commutator. Okay, so let me put the psi's first. Psi, okay, AH comes first, then HA, psi, okay, and plus 1 over, well, just this dA dt, okay, with respect to psi. Okay, so again, for the rest of the semester, we'll just assume this is 0. Okay, there's no time dependence of the operators, like the momentum operator, energy operator, things like that. We never put time dependence in it. Okay, so here you see the time dependence of expectation value of an operator is not going to change if A commutes with H. Okay, so we get this result that d dt of A with respect to psi is equal to 0 if, okay, A commutes with H. Okay, and okay, so then we say A, the operator A or the measurement A, whatever it is a constant of the motion. Okay, so for example, if we have a system in which the momentum commutes with the Hamiltonian, then we say momentum is a constant of the motion. Okay, so if for a free particle, for example, I have h is p squared over 2m, momentum is just p, so p commutes with itself, so momentum commutes with p squared over 2m, and momentum is a constant of motion. So momentum, any expectation value of momentum for any wave function is not going to change with time. So momentum is a constant of motion. But if I have, for example, something like a square well, right, in which case h is equal to p squared over 2m plus some potential, v of x, p will commute with this kinetic energy part, but it will not commute with this part, okay, because p and x do not commute. So for that case, momentum is not a constant of the motion. So that's why when you calculate the expectation value of the momentum, okay, for a certain wave function, you get oscillatory behavior, right? That's because momentum is not a constant of the motion. Okay, this is clear? Okay, how much time do we have? Okay, good place to stop. Okay, let's have our break and we'll go on.